Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'd like to welcome everybody to our workshop. I was really excited to have you all here. So one of the things I wanted to point out is that we'd hope to limit the number of chairs in the front so that everybody would come and sit together, but it kind of had the opposite effect. Now everybody's pushed to the back of the room. So please feel comfortable getting up close and personal with Ashish. Yeah, let's see. A few logistic issues. I hope you've already found the Wi-Fi. It's available here. There's a Wi-Fi network called MSFT Open. You can hook up to it. I see a bunch of open laptops, so I figured that's been figured out. There are drinks and restrooms off to the side. And with that, we'll get started with the tutorials. There'll be a more formal introduction tomorrow morning when we get into the sessions. So it's my pleasure to introduce Ashish Vaswani here today. Ashish finished his PhD at the Information Systems Institute at University of Southern California under the supervision of David Chang and worked closely with a number of interesting people there, including Kevin Knight and Daniel Marcoux and a bunch of great guys doing machine translation. He was also one of the early entrants into using neural models for machine translation, both for the language modeling aspect and for the translation modeling aspect. And so we've invited him here today to give a tutorial on some of the conventional language modeling techniques that have been around for decades, as well as some of the more recent and effective entrants with neural approaches. And with that, I'll let him take it away. Thanks, Ashish.
Thanks, Chris. So does this mic work? Okay, great. Thanks. So hi, yeah, I'm Ashish, and I've been doing some work on machine translation at ISI, and part of my thesis work was on neural language models. Thanks for coming. But before I start, could I get a show of hands? How many folks here are from software engineering? Okay, great. No, this is great. I was going to ask all the NLP people to leave because they're just be bored. And how many have been exposed to language models? Great. And people have used neural network language models here as well? Oh, great. Okay, cool. So it seems that people here have had exposure. So there's a lot of material in here, and I'm definitely not going to go through all of it. It's more like a guided tour. So anytime if you, I'm going to ask, feel around. If you want me to go faster, I will. And if you want me to slow down, feel free to let me know. And please interrupt me with questions. I would like if this is interactive because I'm probably going to learn as much from you as I hope you learn from me. So yeah. So I worked on statistical machine translation at ISI, and what do we do here? So we get a source sentence. We have our. Is there a is there a laser pointer here? Chris or okay, he's not here. Oh, thanks. This is Halloween. I thought a cat would come out of the room or something, but no. So yeah, so this is our machine translation. This is where our machine translation system is. Not quite, but you can imagine it's in this big, little, powerful box. And somebody walks up to you with a source sentence in Esperanto, "La kato sidis sur mato," and you want to translate it into English. The cat sat on a mat. You could also train a machine translation system from say Hindi to English. Vah billi chatai par baithi. And you want to translate it into English again. So it's possible. I mean, I've been told that it would be great if you could have a system such as this. So somebody walks up with a natural language instruction set, A as a sigmoid of Y, and you actually spit out or you translate it into some code snippet. And why did I even use something like sigmoid? You'll find out later on. At least I would like something like this, because I use neural networks, and sigmoids are all over neural networks. There's no reason to imagine that this problem couldn't be reversed. So you get code, and you want to generate natural language. And I've been told that there's a lot of you could possibly get a lot of alignments for code and natural language from sites like Stack Overflow. So I'd like to point out that machine translation really took off because we were able to get a lot of parallel data for sort of input sentences and output sentences, and we were able to train systems. We were able to train statistical systems that were able to leverage all this data and learn to translate well. And it seems that might not be an issue, or you can correct me. that you could potentially get a lot of data. So this might actually be possible, and hopefully we'll see how some of these things could some plans or some systems could be built over the course of this workshop. Here's sort of a more traditional non-neural network-y type instruction loop over all people, and you want to create this for loop here. Okay, so where do language models come in here? So I talked about statistical machine translation. So this is kind of a cartoon of what sort of the important components. So you have this decoder, which shows that computer there, and you get an input sentence, and you want to spit out the output sentence. So now we have sort of two main components here, the translation grammars, which are these. So what happens is the decoder sort of walks over the sentence. Different decoders walk over the sentence in different ways. But basically, it's eating up the input sentence and it's spitting out an output sentence, right? So your translation grammar tells you which pieces of the input sentence you want to eat up and how you want to and what you want to produce. So here's a little phrase, lakato the cat, in Hindi, and in the previous example we had set A as the sigmoid of y. So for that you could have this little phrase, sigmoid of y translates to 1 over translates to the sigmoid function, and A equals could translate to, set A could translate to A equals. So you have these little pairs of input and output phrases. Now the decoder essentially, based on the translation grammar, sort of searches over all possible translations of the input sentence, and it's the language model's job to make sure that what you're spitting out is the correct, is fluent in the target language. So in this, so if you were translating from say into English, the language model would like to make sure that the decoder is spitting out correct English. In this case, it would like to make sure that you're spitting out correct code. So this is a well, at least for me. Let's say if I was building a machine translation system for code, there is motivation for me to study both how code tokens appear, or which are likely code tokens. When I say code tokens, I mean these words in code. And also, if I wanted to generate description of code, I would like to have a model of what code description looks like. So there's both these motivations. Okay. Also, just to give an idea, we have a lot of data, and all this data actually does translate into a lot of parameters. So for a machine translation system for the Bolt program, where we had I think we had billions of tokens on the language modeling side, words on the language modeling side to train, and we were able to get about we were able to extract 1.5 billion parameters in our language model. I'm going to talk about one of the language model that we use there, and the translation grammars are also quite large. I'm not sure what these numbers would look like for code, but perhaps some of you here might know. Okay, so applications of language models hopefully have motivated you, or at least I try to motivate myself why I might need a language model for code, and I think it's important. But in natural language processing, you use language models in machine translation, speech recognition. Language models are super helpful in speech recognition. Spelling correction, document summarization. You want to make sure that the summarization of the document is actually in English. Sentence completion. And here's some examples. It turns out, so you can do code completion, and I know that there's actually work on joint models. This is somewhat different from language modeling, but it's a joint model of code and language by Alamanis et al. And they used it to retrieve. They used their models to retrieve code snippets from natural language queries and the reverse problem, and it seemed to work well. And there's work by Prem and his group also of identifying buggy code by simply training language models and identifying which, how can a language model actually identify buggy code? So there's work on that too. So work is being done on using language models and sort of related models. Okay, so as I mentioned, there's a lot of material, but kind of what I would the goal of this would be for everyone here to get a sense that language modeling is possible. We have sort of two paradigms, the old and the new. Actually, sorry, we have two paradigms. I would like to call them the count-based and the continuous type language models. And turns out that the continuous language models are fairly new. And I'd also and to give you an idea of how what they do to train their parameters, and probably you might get ideas of how to use them in your own work. So today's tutorial, first I'll just define what a language model is. It's you probably already have a good idea. Well, actually most of you do have a good idea. And the first part would be discrete language models are the standard count-based language models. How do you, all language models have parameters, or rather all models have parameters. And so the parameters are probabilities, how we're going to estimate them, what is maximum likelihood estimation, and this is the key. This is in the count-based models, smoothing is the most important part, to assign. You want to make sure that you don't assign zero probabilities to your test data or to events that you actually want to test on. And then we'll go into continuous language models. Sort of the key difference between these two is going to be how they smooth. I think that continuous language models are interesting because they have smoothing built into the model in a more elegant way. And you can think of neural network or continuous language models as great smoothers. I'll talk about feed-forward neural network language models and the new rage recurrent neural network language models. People have been using them for everything, like to do your shopping. Sorry, that was a joke. So I'll talk about two. Hopefully, I will get to talk about two kind of variants. And this is a bit more adventurous. People in the LSTM world or the recurrent neural network language world have been training these enormous language models, and we're unable to interpret them. So I'm going to scale down to these recurrent language models with just 1 or 2 hidden units. And we'll try to visualize them and see what they're doing. So perhaps you could get a sense of what kind of power they might have. This might be interesting to some of the natural language 4K as well. OK, so what are language models? Here in this tutorial, we'll be dealing with probabilistic language models. So we're given a string, and the job of the language model is to assign a probability to that string. So if you're using probabilities, then the correct way to assign probabilities is using the chain rule. It tells you how to actually break down the joint probability of a large string into conditional probabilities. So you go over every single word, and you predict and you compute the probability, or you use the probability of the word given the entire context seen so far. So formally, chain rule is defined here as a joint probability of the string is a product of the probability of the word given all this context. Now you can imagine that gathering data for such long strings is impossible. I mean, gathering data in general for count-based, gathering all possible data for all possible engrams is in general very hard, and I'll briefly talk a bit about it. But here it's much harder because as your sentences get longer, these contexts become more and more unique. So typically, what we do is we make some simplifying assumptions, or Markovization. So you can think of Markovization as binning. So all we're doing is we're taking context and we're binning them into these little classes. So, for example, this is also called a bigram language model because we're only looking at one previous word. And to give you an example of binning, here is this context, the cat. And there's only one word appearing before cat, so we're actually using all the context that's available to us. But for Matt, we had all this extra context, and we only looked at one previous word that ended up binning these two contexts together. So you can think of this so Markovization is just binning, and it's based after Andrei Markov, who's, I don't know if he was the first person to use language models, but he used language models maybe in the 1900s. Does anybody know? OK. So you can also think of a trigram language model where you condition on more context words, so on and so forth. OK. So this is sort of the expression, the formal definition. If you want to compute the probability under an n-gram language model, you make these simplifying assumptions, and you say that probability is just based on the previous k words. So all language models, all these probabilistic language models that I will be talking about, essentially compute the probability of a sentence in this fashion. They go over each one, they go over each word, and they predict the next word. All right. Now the difference is going to be in how these two models, the discrete models and the continuous models, actually compute these probabilities. So both of them compute probabilities the same way. OK, so discrete space language models or count-based language models. There's been a lot of development in this area, from Fred Jelinek, Josh Goodman, Stanley Chen, Turing. And there's been a lot of years have been put into training very good models that are based on counts. And what do I mean based on counts? So let's look at a simple way of actually estimating probabilities based on counts. So imagine you see this, you want to compute the probability of on given sat. So you just count the number of times this bigram appeared divided by the number of times the context appeared. And that's the probability. So it's an easier notation, or notation that's probably going to be useful later on, is you just represent count by c. OK, so now more formally, again, the probability of a bigram is the count of the probability of a word given a single context. The bigram language model is the count of the bigram divided by the count of the context. And to give an example, let's say we have these 3 sentences: the cat sat on the mat, the dog sat on the cat sat on the mouse. So in this case, the context "the" appeared 6 times, 1, 2, 3, 4, 5, 6. So the count is 6, and cat appears after the context thrice. So on and so forth. You just go over the data and you collect these counts. If you had and again, as I mentioned, if you want to compute the probability of a sentence under this model, you just go over every bigram in this case, because we're only looking at one previous word, and you essentially just multiply by the probability of these bigrams that you just obtained via counting. Was that clear? Okay, great. So if you had a trigram language model, you do slightly better. And it turns out that if you increase the number of n-grams on your training data, you will just keep improving. You can use so the probability of the data, your training data, under an n-gram model is greater than the probability of the data under an n-1 gram model. You just keep improving on training. You can use the log sum inequality to show this, but this is not, and I'm going to talk about later why this is not a good idea. Why you shouldn't just keep doing this. Why you shouldn't just always improve probability on training. So now that we have a way of computing, learning at least one kind of language model, this is not the right kind of language model, but we have an idea of learning one kind of language model. So every model that we learn, or every model in natural language or anywhere, should be compared. Because we want to use one model that's better than the other, and language models are no exception. So how do we typically, what might be the 2 ways that we compare language models? So first, it's, you want to carve up your data into training, development, and test. Training, you get your, so for the example so far, from training you get your counts. In development, you can sort of tune what's the n-gram size. And in test, you actually compute how well this model does on your test data. That's unseen. That was not a part of training and development. So this is kind of your data splits that you would do. Now so language models are typically are not useful by themselves unless you just want to generate from them and have a chuckle at what they generate. But typically we want to use them in some task. For example, machine translation. So imagine you have 2 models, A and B, and you have some end-to-end tasks, machine translation or speech recognition. So you use these language models, you evaluate the accuracy, and you get a sense of how well they're doing. And you probably might get a sense of what might you want to improve as well. Maybe you're missing out on some important trigrams or something, or you're not assigning the correct probability. But in general, you just keep trying different models, and you run the whole process, end-to-end process, and then you use a model that did the best on your development set. So unfortunately, this process can take a while because you have to wait for your end-to-end task to finish. So an intrinsic way is to just evaluate on some information theoretic measures. So note that what a language model is doing is it's just predicting the next word. So that's how they compute probabilities. So so you can because what you're doing is prediction. You can use a lot of you can borrow a lot from information theory developed by Claude Shannon to actually compute measures that could be useful in comparing language models. Now, I must warn you that there is no reason to think that, it would be nice if there was a correlation between these intrinsic measures and your final task, but it is not necessary. Well, for example, I know, I've been told in code, if you train on a certain project, I know Android apps, and then you test on another one, your language models, your perplexity or your language model trained on one task could be really poor on another task, but you might have tuned the language model on one task based on these intrinsic measures and might just not be a good idea. So I think evaluating them on extrinsic tasks is the right way, but this is certainly faster, and you could tune some hyperparameters based on intrinsic evaluation. So we're doing predictions. One way is to actually compute how likely, so language models essentially want to make sentences in your language. The correct language model wants to say that this sentence is more likely than another one, and the more likely sentence should actually be more fluent in your language. So one way of computing that is you take your data and you actually of correct sentences that you actually observed, and you compute the log likelihood of the data, or how likely does the language model think your true data is. And in a trigram language model, you again go over all the tokens, and you'll compute the probability under the trigram language model. Higher is better. The more likely a sentence, the more probability your model assigns to the true data, the better it is. So you can also, another intuition is how many bits does it actually take? So now you can think, so essentially you have this true distribution, and you're trying to and your language model is another distribution. When I say true distribution, the distribution that actually generated your true data. And your language model is another distribution that you are learning, right? So how many bits would it take if you actually tried to encode, how many bits on average would it take if you use this possibly faulty distribution, that is your language model that you trained, to encode your actual true string? So you can use cross entropy. Cross entropy is a measure of that quantity, and lower is better, because the better your language model is to the true distribution, the less number of bits you'll actually need on average. So cross entropy is a sort of information theoretic sort of message length kind of metric, and people often use perplexity, which is exponentiated cross entropy, for also evaluating. Again, lower is better. And in the slides later on, I'm going to be showing some numbers on perplexity. Okay, so now what I told you was we just go over the data and we just compute counts, and we evaluate our language models using entropy or cross entropy, log likelihood, or perplexity. But do we have a good language model? So what we used was the maximum likelihood estimator. It's just a function from data to models. So you take the data and you spit out a model. So this process of just counting based on training data and assigning probabilities is the maximum likelihood estimator. So it sort of tagged these probabilities with MLE. And the good news is you can actually achieve low perplexity on training, but as I mentioned, your test data might be different from training. But there's a bigger problem. So imagine that your test data was the dog caught the cat, which is just built up of some words from here. And in this person's language, this seems like a reasonable sentence. Now, here, you notice that the probability under maximum likelihood estimator for dog given caught is 0, because that bigram did not appear in your training data. So what's going to happen is you're actually going to assign 0 probability to this sentence. So your test data probability is 0. This is certainly not what you want. You want to be able to generalize. You want to be able to train models that actually don't assign 0 probabilities to reasonable test data. That sentence was reasonable. So one possible solution would be to, let's say, just train n-gram models where the n is small, bigram or unigram. You'll get terrible models. Another option is, well, let's just train on all the data that we could possibly collect, and you will see every possible n-gram. So here's a graph of tokens versus types, and by tokens I mean the number of words that actually occurred in your data, and types I mean the number of unique words. I don't know if the people in software engineering have the same terminology, but we call them tokens, and the number of unique words is types. And I went over. Oh, really?
Yeah, it's very different.
So just forget that. Just think that you're a natural language person. So I took some of our data. I think this was from the Wall Street Journal. It's the blip corpus. I took 8 million lines, and I computed how many types I saw. I was kind of horrified to see that as you increase the number of lines, the growth in types is linear, or at least up to 8. This is for code. This is the Eclipse. Was this the Eclipse code set? Sahil gave it to me. I think he said this is the Eclipse code base.
This was the Eclipse or the Android.
Oh no, this was the Eclipse one. I know that because I actually got it. So, but when I say Eclipse, it's source code for Eclipse.
Yes.
Okay, so this is the source code for Eclipse. So I don't know if this tails off later on, but clearly the behavior is very different. So people in software engineering are definitely in more trouble than we are. We don't have these enormous sort of we don't have this kind of growth in vocabulary. But so let's say that I'm a natural language, and I decided, okay, I'm going to collect all possible n-grams. So there's about 60,000 words when you go up to 8 million lines. So the number of bigrams is, as you can see, these things are going to grow significantly. Now, if you look at the Google n-gram corpus, they have about, this is not clear, but it's about 1 trillion words. They collected data from 1 trillion words. So let's assume we used all that data, and how many possible n-gram counts could we get for each unique n-gram in our corpus, trigram in our corpus? Turns out you'd only get 0.0046 counts for each trigram. So I did some rough calculation. I think the web has about this many words, the indexed web. Well, assuming that all the bytes in the web were just words dedicated to generating words. So you'd get about 2 counts per word. So I guess you could get all possible trigrams. Now, if you use that for code, if you looked at the situation for code, it's much severe. So clearly, the strategy of collecting all possible data is not going to work. So this is the essence or the core of count-based models, or smoothing. Rather, so we know that collecting data is not enough, and smoothing is going to be how you actually move probability from events that are seen in your training to events that are unseen. So smoothing is all about how you move probability mass, and some smoothing algorithms move mass more intelligently than others and actually do better than others. As I mentioned before, neural network language models, I think, have a more elegant sort of solution to smoothing, and we'll see how they do smoothing. But for now, let's look at. I'm going to go over some very simple sort of smoothing examples, and give you pointers to some other advanced ones. Is this clear up to this point? Is it going too fast, too slow? This is good. Okay. No one's sleeping as yet, so I think this is okay. So again, smoothing. So you're taking probability mass from things that were seen and you're assigning it to events that were unseen. Remember in the MLE case, probability of dog given caught was 0. So you assign some small mass. So then this test probability would actually be greater than 0. Okay. So again, data preprocessing, the standard kind of data preprocessing that we do in natural languages, we get split data into train, dev, test. We get word frequencies and keep the top V most frequent words. And why do we do that is because it's quite possible that on our test time we actually might see even a single word that did not occur at training. So we kind of want to assign probability to unknown words or get an estimate of how frequently you can see unknown words. Maybe after some context, unknown words are more common than, yeah.
When you say code, you mean code in a particular language?
Sure. Like say Python or C++. Yeah.
So it's when you say code, it means that it's in a particular language.
Yeah. And I'll have some graphs later on perplexities or cross entropies on some code in certain languages like Python and so on. Yeah.
So what's your interpretation? Why the long tail or whatever it is? Why it's so bad?
So I mean, if I was speaking to you and I just kept on, imagine if I kept on creating words like I kept creating variables. You probably wouldn't understand what I'm saying at all. But variables are need to be more descriptive. For example, I have this variable called there's a weight matrix.
I see what you mean.
Yeah.
Yeah,
it's just you're free to create whatever name you want to a variable. Yeah.
But that's not in the language.
Yeah. At least I hope not. Yeah. Okay. So the simplest form of smoothing is add-one or Laplace smoothing, and what you say is we pretend that we just saw every word once more than it did. So we just add. So this was the maximum likelihood estimate of a bigram, and in the case of Laplace smoothing, the maximum likelihood, the smoothed estimate under this add-one Laplace smoothing is that you just add one count, and to make sure that's a probability, you need to add v at the denominator. So if you go back to this, situation, probability of caught given dog was 0, and under Laplace smoothing, it's 0.11 now. 8 was a number of unique words in our vocabulary. So. Now what happens to the probabilities of words that were actually seen, or bigrams that were actually seen in training? Now, earlier was 1/3, that's about 0.33, and it was lowered. So you can see that what add-one smoothing did was it actually increased the probability of unseen, basically from 0 to something non-zero, but it decreased the probability. In this case, it about halved it. And this is the problem with add-one smoothing. It steals a lot of mass from seen events, and it's probably the most basic and the worst. At least for language modeling, it's not something you would use. But it was one of the earliest techniques, and it's sort of a simple example to show smoothing with.
Just had a quick question for the audience, I guess. Does anybody know what the best kind of freely available identifier splitter is out there?
Well, I guess I have some that I've made available.
Could you just introduce yourself? Not everybody knows
I'm
you.
Dawn Laurie, and so I guess I've spent a long time developing identifier splitters, and I've made mine available. So I found that the camel case underscore kind of traditional one works pretty well, and if you want something that's more sophisticated, I have one, and also Lori Pollock has another one.
Thank you.
Thanks for pointing this out, Prem. I forgot to add that you could do this could be a part of your pre-processing arsenal, splitting up words, and we could conceivably do that in natural language as well. And I suppose you...
I guess when you presented the graph, the first thing that came to my mind was if you had split your identifiers, you wouldn't see that same tail because identifiers are all composed of an underlying same vocabulary. And then especially if you try to remove some of the arbitrary abbreviations that programmers try to introduce, then it would really...
I guess Prem at that point, when he gave me the code, didn't realize that you had an identifier. He would have given it to me.
That's why I asked.
But I did some pre-processing. Prem said just convert all the digits 2 to 9 to just 1. That's the only pre-processing I did. So it's less severe than what it would have been if I didn't do anything. Yeah. But that was more alarming, isn't it? Well, actually, so what do you know what the tail is? So it's certainly not that case. Do you know how many I should expect in 1 million lines or 8 million lines of code?
So I haven't actually produced that graph, but I could look back and see some stuff where I did counting of how the size of the vocabulary once you split, and it changes drastically.
I mean, we've run it on hundreds of millions of lines of code. You get hundreds of thousands of unique words even after splitting. So it's pretty fast.
So I know we have this large corpus called gigaword. It's about 2.4 billion words. When I looked at, and this is language, and I did some simple pre-processing. I converted all the digits to like just an @ symbol, so that decreases the sparsity. And I think if I look at all the words with count greater than 6, it's about 500,000 of those. All words with count, unique words with count greater than 6, there's about 500,000 of those in 2.4 billion tokens of natural language, naturally occurring text. That's the gigaword corpus. It's a large corpus that we use in, yeah.
So I think I ran a pre-processing on Eclipse itself.
Okay.
And the version that I worked with had around 80,000 unique words.
80,000?
Yeah, I just split using camel case and underscore.
Okay.
And there were like about 80,000 different.
Okay, so it's just a bit more than what we had for language. 20,000 more. We saw about 60,000 tokens for about 8 lines. Okay, yeah. So I took about the entire Eclipse corpus there. It's about, yeah.
I was just mentioning the quiz. I don't know how many people know about Heap's law, which says that the number of types basically grows as sort of the square root of the number of tokens.
In code?
I don't know. That in natural language it does. And it's sort of a corollary of this law.
This is Ray Mooney from UT Austin. Just so everybody knows everybody.
Ray, you're speaking out of turn. You're supposed to say things in the neural network part. Sorry. Okay, so smoothing is necessary. Here's a simple example. Good Turing smoothing is somewhat more advanced and it's a bit more intelligent. It says it moves probability mass from counts that occur, from n-grams that occur C+1 times. So you kind of look at frequencies of frequencies here. So you look at the number of, so you actually see n-grams that occurred C+1 times. That is the frequency, the C+1 is the frequency of those n-grams, and you move. And for the unseen n-grams, you move probability mass from the n-grams that occurred once, and which kind of makes sense here. The count of the if the count of the n-gram was 0, then you would move probability mass from those n-grams that occurred once. If the count was 2, then you would move probability mass from n-grams that occurred thrice. And essentially, this is the formula. To give you an example, so this is an example from Josh Goodman. So imagine that. That formula would be more clear in this setting. So you're fishing in a lake, and there's 8 species of fish: carp, perch, whitefish, trout, salmon, eel, catfish, and bass. And you catch 18 fish. So that's your data that you see. In this case, it's just unigram because you're only catching 1 fish at a time. And so you catch 10 carps, 3 perches, 2 whitefish, and 1 trout. 1 trout, 1 salmon, and 1 eel. And how likely is the next species a trout? Well, if you use the maximum likelihood estimator, you would get 1/8 because out of 18 fish, you caught 1 trout. Now, how likely is the next species new? Now, what the good Turing estimator does, it looks at the number of, this is unigrams, so it looks at the number of unigrams that actually occurred once. There's 3 of them, and it assigns this probability to any unseen unigram. In the case of a bigram, it would do the same thing, the number of bigrams that occurred once, and it would assign that probability to unseen bigrams. So if you went back to, certainly when you move mass, the probability of a trout before, in the maximum likelihood estimate was 1/18, now it'll be less than 1/18. So the good Turing probability of things seen with 0 frequency is the number of things that were seen with frequency 1 divided by the total number of things that were seen. So here's just a sort of visualization. Now, bass or catfish were unseen, so their probability now would be 3/18, and in the case of trout, it's reduced. It's 1/27. So smoothing. the most popular models for language models for smoothing and language modeling are the back-off and interpolation models. Actually, most popular interpolation models, they generally work better than back-off. For code, it's the cache models, and I'll talk briefly about cache models. So in back-off, if an n-gram is sort of frequent, you use its count. Or if it's not seen, I guess I should sort of rephrase, this is incorrect. If an n-gram is seen, then you use its count. If it is not seen, then you use a lower order n-gram count, the count of a lower order n-gram. In interpolation, you kind of mix all the context, and the probability of a word given some context is a mix of the probability of a word given all its possible shortened contexts. In interpolation works better than back-off, and if you sort of wanted to see the kind of formal definition of interpolation, imagine you had a trigram language model. You were trying to learn a trigram language model. The interpolated probability of a trigram would be a mixture of the bigram, of the trigram probability, the bigram probability, and the unigram probability. And because you want probabilities, you need to make sure that this sort of the weights of this mixture sum to 1. You can also condition these interpolation weights on context. That works better. You can have lambda as a function of the context itself. Lambda 1, lambda 2, and lambda 3 could be a function of the context itself. So some interpolation algorithms that I'm not going to go into detail are Jelinek-Mercer, absolute discounting, and the most popular one and the most successful one for natural language, modified Knizzernai. We use modified Knizzernai for our MT experiments. So to give you an idea of how well these algorithms actually do on sort of a, this data set was, I guess it came from the 90s, and it's about 1 million words of training data. It's about 70,000 to 80,000 tokens of development and test set. And you can see that the Knizzernai 5-gram language model actually does the best among all these other smoothing algorithms.
Sorry, one question. So the perplexity here
yeah.
is the cross entropy.
2 to the cross entropy.
It's
2 raised to the cross entropy, yes. And lower is better. So perplexity is sort of an idea of how the language model is less surprised at seeing the test set. The smaller the number, the less surprised you are. So it turns out cache language models actually work quite well in code. So there's this paper on the naturalness of buggy code by Ray et al. It's Prem and his group. And what they did was they actually looked at, they used cache models to inspect which code was buggy and which was not. And it turned out that buggy code had higher entropy, in this case more perplexity than non-buggy code. And why is that? So in code, these variables keep popping in and out of scope. So you kind of want, it would be nice to actually have a history of which variables appeared in the context. So what the cache model expression is that the probability of a word given some history is the n-gram probability under your standard n-gram model. This could come from anything. It could come from a modified Knizzernai model too. Given and it's a mixture of the probability of the word under the history where you define what this history is. And Stefan Fiot was kind enough to allow me to publish these results. He's a student of master's students with Charles Sutton. This is his master's thesis. And I don't know if this is clear, but this is the cache model, and you can actually see it. This is a competing n-gram model. This is the cache model, and this is another n-gram model. I think this is a Knizzernai language model, but he showed that the cache model on C, Java, Python, and JavaScript achieves the lowest cross entropy. So remember that cross entropy is a number of bits. It would actually take you an average to encode a piece of code under the model. Lower is better. So you achieve lower cross entropy on it's about 1 billion lines of code here. No, it's 100 million lines of code, and you see that the cache model actually achieves the lowest cross entropy. It achieves better cross entropy than other language models. So I can send you Stefan's email. I have it, and you can contact him for more details. But it seems that for code, cache models are better. Sort of to summarize, what is a general training approach for these n-gram models? We collect n-gram counts from our data, and we smooth for unseen n-grams. You can use your favorite smoothing technique. We do end up with a large number of parameters because you at least have as many parameters as the number of unique n-grams that occurred in your corpus. But the advantage is that these probability computations are quite fast at test time because you just have to do lookups. So again, so the model size is large, but you have really fast training time. For Knizzernai smoothing, there's I believe Kenneth Heafield has released a toolkit that trains these models really, really efficiently and really fast. And certainly querying time is also very fast. I think we've been going really fast here. So what do you think, Chris? Do people want a short break before we move to the next section?
This is like a natural stopping point. We could peek outside and see whether there's some coffee break food available. What do you guys think? Do you want to keep continuing, or would you like to take 10 minutes to have a drink and restroom break? Don't everybody speak at once.
Maybe I should ask for a break.
Yeah. Okay, let's give Ashish 5 minutes. Feel free to get some food and drink, and then we'll pick up.
Thank you, everyone.
A little bit after 2. Thanks.
Okay, so we're going to go to the next part of the talk, and this is something that I'm excited about. I've done research work here with my advisor David, who's actually in the audience, and so these are continuous space language models, and so to sort of a bit of motivation, we noticed earlier that perhaps the most important part of what we looked at earlier was smoothing. The language model's job is to just assign probabilities, and smoothing was crucial in these count-based models. And so the good news here is that we'll actually see a nice model which has smoothing built into it. And the bad news is that training these models is hard, but again, we'll be happy because there's solutions to that, and models train really well. And I'll show techniques to train these models, or at least one technique that's quite successful in training these models very efficiently. Okay, and then towards the end, we'll move to recurrent neural networks that are the rage right now, and they sort of free you from this dependency on fixed contexts. So remember earlier we talked about bigram, trigram. Here it's whatever gram. Ideally, it should learn which words are important in the history, and we'll talk about those. So first, feed-forward neural network language models. These are again sort of finite context, now imagine you were kind of training a trigram. Here's a little motivation. You were trying to train a trigram language model, and in your training you saw Apple was sold, but you never saw the string IBM was bought. So if you want to predict bought given caught, I mean the count of that n-gram is 0, and you would assign 0 probability to your test data. But we do know that I mean if you had an idea that bought is similar to sold, it's an action that you might do in the stock market, and IBM is similar to Apple in that it's a company, could we actually use this information to sort of transfer probabilities? So if we knew that sold is likely after the string Apple was, then could we somehow, and by having this knowledge, could we transfer that probability to unseen strings? And kind of n-gram language models will do that. This is like sort of a nice clean way of doing smoothing. And you will also see what these notions, what does it mean to be similar in a neural network language model. So neuroprobabilistic language models or neural network language models were first introduced by Bengio in 2003. And you can think of a neural network as a feed-forward neural network as nothing but just a bunch of matrix multiplications and nonlinearities. Also, these slides might be a bit more involved, so we can stay on a slide for as long as you want. So feel free to ask questions. Okay, so now the important part is in neural network language models. Sure, you feed in words just as let's get the pointer.
How do you know, I mean, Apple is similar to IBM and
Sorry,
bot is similar to...
Great point. So I should have mentioned that we will also learn that automatically.
Okay.
I mean, the hope is that IBM must have occurred somewhere in your data. I mean, if IBM didn't occur anywhere in your data, then we wouldn't learn it. But I guess the situation was that you haven't seen this particular string, but certainly you've seen IBM in your data being used in some context, and you've seen bot being used in some context. Otherwise, you'd have no hope here. But you've seen these things, and the model should hopefully I'll convince you that the model can learn such similarities. But yeah, it learned automatically. Yeah, that's a good question. Thank you. Okay. So again, similar. So remember that all we're doing is just like we're probabilistic language models. So what we need, our job is to compute, the neural network's job is to compute this probability. And here's how it's going to do that. So you feed in the words just as you did. This is the context, the cat. Now the only difference, now the sort of one big difference among others, but perhaps this is an important one, is that words are represented inside the model as vectors. So you can think of it as like a dictionary. So when somebody walks up to you with the cat, you go to this dictionary and you look up the vector for the. In this case, it's a 3-dimensional vector. It's also called embedding. We don't use. I mean, we're trying to stop using the word embedding in natural language now. It's really overused. But I think I'm safe here. So we call them input embeddings.
And so, what's the intuition behind using embedding?
Oh, what's the intuition? So you will get this kind of. So one intuition is that. You hope to learn similarities between words that are related, and because you're putting words in this high-dimensional space, and you might be able to learn similarities because words in this vector space might lie close to each other. Now, imagine if every word was just you can represent a word by just having let's say a vocabulary had 5 words, right? And you can represent each word by just a one-hot or 1 of k representation, where each word is just represented by 1 in that position for that word. For example, there's 5 words in this vocabulary, and there's 5 words in this, and cat, the is represented as 0, 1, 0, 0, 0, and cat is represented as 0, 1, 0, 0, 0, 1, 0, 1, right? You can represent any word like that. Take an arbitrary vocabulary, and you could do that. Every word is distance 1 from each other. But that's kind of ridiculous, right? Oh, well, I mean, that doesn't help you much. So the hope is that by actually doing this, by putting words in this space, this vector space, and by you at least are allowing the possibility of learning similarities between words. Now, how we're going to learn that similarity, I haven't told you yet, but at least you're allowing that. Right here, all words are sort of quite similar to each other, equidistant to each other, in this kind of representation, also called the 1-hot or 1 of k representation. But while here, when these are kind of real numbers, maybe it's possible that cat is 0.1, 0.2, 0.1, and dog is 0.1, 0.3, 0.1. So the Euclidean distance is just 0.1.
So just for clarification, you get those other numbers by kind of co-occurrence?
You learn them.
But you learn them according to co-occurrence.
Yes, yeah. So what we do, so I haven't talked about training as yet. That's going to come up. The models are automatically going to learn it. So in some sense, you can think of that if you sat down and you decided to write down. I mean, perhaps this point will be clear later on. But hold on.
The intuition is that if words appear a lot in similar contexts,
correct, yeah,
they have similarity on some of the parameters of those words. Because they're not synonyms, of course, like apple and IBM. But then on many parameters of that, they're similar. So in this multidimensional space, they will be kind of closer on those parameters.
Great, thank you. Yeah. Yeah.
And so in this case, can we say input transformation instead of embedding?
Yes, sure, absolutely. Yeah.
Is the same intuition.
Yeah. Input transformation. I'm transforming it to an n-dimensional, or in this case, 3-dimensional space. Yeah, transformation.
So it's an embedding into another space.
That's right. Yeah. So I didn't realize that the word embedding would cause so much confusion, but yeah, it's a transformation. Yeah. Okay. So now I'm going to show you how we will compute the probability of sat given the cat. So we take these context words as is. We sort of look up their embeddings. So now we get this sort of two 3-dimensional vectors, or you can think of it as 1 6-dimensional vector. And each one of these arcs is actually, each one of these connections is actually a weight that needs to be learned. The model needs to learn these weights. So now you apply matrix multiplication. You multiply this weight matrix by this vector, and you get in this case a 6-dimensional vector. So I should probably say, so you decide on how many dimensions you're going to have for the words, how many hidden layers you're going to have in your model, and what is going to be the dimension of the output word as well. So we'll talk about what do you mean by dimension of the output word. But for now, we're sort of computing what the probability of a word given context is, and we're here. So now you get this hidden representation of this context. Now we apply nonlinear. So in neural networks, we typically apply we apply nonlinearities, and you can have you can apply the nonlinearity of your choice. The normal functions are the typical functions are sort of hyperbolic tangent functions, or sigmoid functions. I'll have graphs of those later on. There's these other functions called rectified linear units. I'll talk about them as well. Here's so now you apply. So now you try to you could have potentially more hidden layers because you want a better representation of the context, and we sometimes observe that adding more hidden layers actually could give you better performance. So I should put a disclaimer. I don't fully know what's happening inside these hidden units. All I know, I do know that it's somehow able to represent this context so well that it's able to produce, so that neural networks are able to produce reasonable probabilities for output words. We're able to look at what happens, how these input dimensions for these words look like, and how words become similar in this input dimension. But it's still a sort of a mystery as to what's happening in these hidden layers. Later on, I'm going to show you examples of very simple models where we can actually see what's happening in these hidden units, but I haven't really stared at how is the cat similar to the dog in this particular hidden layer. Yeah.
So I'm just wondering whether there are specific studies, either in vision or speech recognition or anything like that, that test specific hypotheses about how actually what is learned is being represented?
So in vision, yeah, people do kind of visualize what might this. So in vision, these multi-layer networks, people have been able to show that neurons, they could also call them neurons, at lower levels learn to be edge detectors, and higher level neurons kind of learn to combine these edges and to learn more complex sort of patterns. And so each layer learns a more abstract representation of the input.
I see. And these are statistically verified. These are not just guesses. I mean, not just
they're more sort of. I think what they do is they try to see what kind of inputs excite these neurons the most. But I don't know if there's any statistical analysis there. But perhaps other people who could point out.
So I don't know about the statistical analysis, but one thing to watch out for those image results is they specifically use convolutional neural nets where the connections are a lot less, and it makes sense because stuff is close together, and stuff is close together in like Euclidean space. So if you can figure out that stuff is close together in the language networks, you can use convolutional, but it doesn't always work. Like the spaciness of the whole thing doesn't always work. And the reason why those visual neural nets really work out and they can show those little groups is because they've dropped down a lot of the connections in those neural nets. Most of the gains in the image space have been done with the convolutional neural nets because the search space of the fully connected layers is way too high. Once you drop it down, it's a lot less and you can get better results a lot quicker. That's my understanding. I'm not really great at this, but whatever.
Thanks. So again, you'd apply. So once you've got this hidden, you take this vector that you obtained and you apply it on a nonlinearity, and now what we have is the final layer, the penultimate layer, gives you a summarization of this context in this case a three-dimensional space. Now, how we actually move from there into computing word probabilities is, again, similar to the input. Each output word is also represented as using a transformation, as in this case a three-dimensional vector, because the last hidden layer had 3 hidden units. And you compute scores by taking the dot product of this vector and this embedding of the word, and you exponentiate it. So this actually gives you the unnormalized score of this particular word given this context. It's not a probability as yet. If you sum over all the words, this quantity is not going to sum to 1. Now, if you want to compute the probability, then you actually have to compute this normalization constant. So you have to go over every output word, and you actually compute this dot product, exponentiate it, and that gives you your normalization constant. And if you want to, and then you finally divide this unnormalized probability by the normalization constant to get a probability of, in this case, sat given the cat. As I mentioned, nonlinearity that I found to be quite useful or works quite well is this rectified linear unit, and here assume this is your these neurons are both rectified linear units, and so if your input which is on the x-axis is 0 or a negative number, then this neuron outputs 0, and if it's positive, it just basically outputs that particular it outputs the input itself. And there's been some very recent work on how these rectifier linear units are actually carving up the space. But if you use there's other nonlinearities, which I will show graphs of later on. I should have probably shown them here. Like these sigmoid functions, they have these problems with gradient. The gradient becomes really, really small. And I already said gradient, but the way you train these networks is by you compute gradients and you update the parameters in the direction of the gradient. And when you have these squashing functions like sigmoid or tanh, you can get problems with gradients. Rectifier linear units don't have issues with gradients. And empirically, empirically, they've been observed. They've actually done really well. And the language models that I've used, the language models that my toolkit implements, or this is in collaboration with others, uses rectifier linear units. So that's how we compute the probability of a particular word given a context. Yeah.
So the rectified linear units, are they different than the units that was used in semantic hashing?
This is why what was the
They said something binaryized. I think they pushed it to 0 to 1.
Okay,
they didn't have a middle ground. So these ones, they're either 0 or they're positive non-zero.
Yeah, positive non-zero. They're either 0 or they're the input.
Okay.
Yeah, and so kind of these are one of those landmark things in deep learning where switching from these standard nonlinearities to rectifiers actually improved accuracies on many tasks, which include in vision as well. So. There's some motivation from biology that neurons tend to behave similar, but I don't know much about that, and I'm not going to go into that either. Yeah.
Abram, I think in that semantic hashing paper, what they actually used was a conventional.
Can you speak a little louder, please?
I think they actually use a regular sigmoid or tanh, but what they do is they use this trick where they actually will bin them according to their magnitude.
Okay.
So if it's between 0 and 1, if it's 0.1, they'll actually call that a 0. If it's 0.9, they'll call it a 1. So it's this rule of thumb of, rounding it according to its magnitude.
Okay.
I see.
All right, thank you.
Thanks. Yeah.
And can you go back, please? Can we skip the green or the brown layers?
Yeah. Oh, which one? These ones?
Yeah.
So
which layers are really important here?
So typically what happens is that your hidden layer is the most important layers. If I were to say, I think you should have at least these many layers. So what this stops. So what this is doing is that now typically these layers are very large. They could be like say 1,000. And if you were directly connecting the input words to the hidden layer, so notice that there was no nonlinearity here. This is just two matrices multiplying, right? So you could potentially reduce it to just one single matrix, which is the multiplication product of these two matrices. And in fact, that's what you do at test time to speed up things. But why don't we just use one matrix from the hidden layer to the input, right? So these dimensions are quite large. So imagine if you actually wanted to do that, you'd have to have 1,000-dimensional embeddings for each word. So this kind of breaks it into a two-step process where you compress them into a smaller dimension, and then you transform that into here. But if you ask me the most important, you should have at least this many, and you have to have that because that's the output. Yeah, I mean, adding hidden layers one after the other, you could empirically test that on your development set and see what's working well.
There's a lot of interesting research in this area, like how many hidden layers do you need? Theoretically, anything that you could learn with multiple hidden layers, you could also learn with just a single hidden layer.
Right,
but if you train it with a single hidden layer, oftentimes it doesn't learn as well. So there's some interesting work by Rich Caro on taking really deep models and replicating them with shallower models and all this. This is black arts, though.
But it's also interesting in that case, the funny thing was that they did not train the shallow network on the actual data. They trained the shallow network to model the deep network. So it's funny that you couldn't train the shallow network. So there's two networks, A and B. Eventually, they trained A and B to be the same quality, right? B is the deep network, A is the shallow one. You could not train A to be as good on the actual data than if you trained it to fit the deep model. So it's a two-step process. You fit this deep model, and then you take a little shallow model and you try to fit it to the deep model. And you actually get the same you get the same accuracy, but you're not able to train the shallow model in the original data. So there's this guy, and when I say fit, I mean it doesn't fit. It actually tries to match it to the output distribution. So somehow learning this process of mapping to the distribution is easier for the shallower model to do than to actually map to these other, because the output also are categorical. They're one-hot variables, so it's easier for it to do that. But I don't know if there's a strong Is there a strong, like a very sound theoretical underpinning of that? Okay. So sorry, I just want to point out one thing. I will mention a citation later on about work from Kenton Murray and David Chang about auto-sizing these neural networks. There's a paper last year, and it'll be cited, and you can actually, it's been implemented as a part of our toolkit, and you can actually learn the size automatically. So it's cute. Yeah.
Just curious. I mean, I assume once it's all trained up, right?
Yeah.
And then using it for something like finding bugs or whatever, right?
Sure.
Does it really matter whether it's deep or shallow as far as the performance is concerned?
No, it just matters. I think it. Oh well. I mean, so does it matter? What matters is you trained a good language model. If you actually went ahead and trained 10 layers and it was better than you're training 1 layer, then sure. That's what matters, right?
But performance impact is somewhat there, right?
Sure.
Like, so some of the things that have been critical about shipping neural net models
Right,
and empty systems are to minimize the amount of multiplications you need to do, right?
That's right. So if I'm doing real-time
I
segregation of code, right, I might want a really super fast model, and
I see. Sorry, I guess you meant the query time implications of this.
Yeah, exactly.
How expensive is it to query? Yeah, the more matrix multiplications you have to do, the more expensive it is.
So the shallow models are better.
Sure. Well, I don't know if a shallow model ends up having like 50,000 units versus having 4 layers with just 5 units. I think the deeper model is certainly faster.
Well, what Rich does, he keeps the number of parameters the same.
Yeah.
But how much faster? I mean, is the performance that much different that it would take a really long time versus a short time to, if the friends?
Well, so I don't have comparisons from between different sizes, but it depends on the complexity of matrix multiplication.
Training takes a long time, but then kind of using it for predicting is just one.
Yeah. I don't have that's an interesting question. I do not have an analysis of running time versus layer size on some test set query time. But I'll talk about something later on that actually speeds up test time. So these models are particularly notorious for query time, simply because you need to. I'll talk about how to speed that up quite a bit as well. So I saw another hand come up. Yeah.
In terms of real-time performance, like I've used these things for real-time computer audio, and you really want to keep them small. Like a brain that's bigger than 200 megs of doubles or floats is oftentimes really hard to run on a CPU in real time when you're asking for more than, so it's about 200 megs, and you need at least 200 responses in a second. That's hard to push on a CPU. If you had it on the GPU, you might be able to do it, but you could blow out your I/O and just not be able to do it. It might work better on the GPU bigger and just in batches, but it might not be real time. So there is a balance, and like I have the number of features in a lot of cases, or I have the size of network, trying to tune it down there. So performance is an issue, but you got to experiment.
Because when we train our systems, we don't deploy. Right now we're on a project where we actually have to deploy it in an online setting, but we typically sort of have these static evaluations, and there are time cutoffs, but I don't think they're as severe as we need to sort of cut down every second. Perhaps they'll be more important in a commercial setting. He mentioned GPUs. GPUs have really allowed you to train large-scale neural network models because you can do fast matrix multiplication, especially if your inputs are coming in batches versus one input at a time. So that's definitely that's one of the reasons why neural network research has progressed quite a bit. But again, I'm going to talk about something interesting later on that avoids this expensive query time, and that is quite fast. So again, remember the fact that we have to in order to compute a probability, we need to compute this normalization constant, and we need to divide this by the normalization constant, which can be quite expensive because if your vocabulary is say 100,000, you have to go over 100,000 words. So probability of a word given context is its unnormalized probability divided by the normalization context. So in this case, how do we train the model? We find the model that maximizes the log likelihood of your data, the data that your training data that you've seen. You can typically what people do is they have a validation set too, and they sort of stop at where your perplexity on validation actually starts decreasing, or they run it for 30 epochs and pick the model that achieved the best perplexity and validation because you don't want to overfit in your training, similar to what we talked about before. I guess, right, so what is maximum likelihood training actually doing? So maximum likelihood training of these models is very expensive. And why is it expensive? So imagine this is your word, and these are all the words in your vocabulary. So what ends up happening in maximum likelihood training is, I mean, if people want to talk to me about the details, I have slides of them, but they'd probably be meaningless here. This is a much nicer sort of intuitive visualization. So this is your word that you've actually seen, and you're not seeing any of these other words after the context. So what maximum likelihood estimation tries to do is, tries to make this word probable and every other word less probable. All the words in your vocabulary. So essentially, it has to go over every single word in your vocabulary to make it less likely, which means going over the embedding of each and every one of these output words. That's an expensive process because you could have, as I mentioned, you could have really large vocabularies. So how does it train? You do stochastic gradient descent. You compute. So this process of actually computing the probability given the context was called forward propagation, and this process of computing the derivative, or computing the derivative of this objective function, is you can compute that using this process called back propagation. It's just a matrix way of doing the chain rule in derivatives. And if you're doing maximum likelihood training, unfortunately, you can have very slow training and decoding times. So what's happening in, what's sort of the assumption in maximum likelihood? So you assume that your observed data has been generated from this true distribution. That's your training data. And you're trying to approximate this true distribution that actually generated your data. So something that I've worked on, along with a couple other folks, is a much more efficient way of training these models. And it's called noise contrastive estimation. I should have the citation later on. It's two Finnish gentlemen, Gutman and Hjärvinen. This is a technique that they invented, an estimator that they invented. And what happens here is you assume that you not only have observed data, but you also have noise. And this noise is generated from a distribution that you know. It could be the unigram model on the training data. It could be the uniform model on the training data. But you know this distribution, and what you're doing is you're injecting noise data into your training data along with the observed data. So your data essentially expands, and you inject k for every true word. You inject k more noise samples. So you have more noise samples. You have more. So you have. And essentially, you can think that your training data now is k times your original training data. So if your context was the cat and the output word was sat, then these could be your potential noise engrams: the cat pig, the cat hat, the cat on, so on and so forth. Now what noise contrastive estimation does is, so now this is your true word, and these are your noise samples. Notice there's only k of those. There's not, I mean, this is not as, I mean, you could make k as big as a vocabulary, but then we don't. It turns out we just need about 100 noise samples seems to be enough. So you have your true word and you have k noise samples, and what noise contrastive estimation is doing is it's just trying to classify this word as being true, and classify this word as actually coming from the true data, and correctly classify these words as coming from the noise data. And that, by trying to maximize this classification accuracy, you end up training your model. So if your neural network model becomes good at this, it also becomes good it also becomes better at predicting the next word after a certain context. This method is so the estimator itself, noise contrastive estimation, it's far more general. It's you can think of, so I know that people in code, Lamanis et al. Have actually used it they've used noise contrastive estimation for joint modeling of code and language. And I say it's general because any type of model that you have this issue where normalization constants can be super expensive to compute, you can use noise contrastive estimation as an alternative approach. And it works quite well, especially in language modeling. So this is joint work by, I guess, so this is, and unfortunately, the citations are coming later on, but so we adapted noise contrastive estimation. So noise contrastive estimation is a Finnish invention, and Andri Min and E.Y. Te adapted it for language modeling, and we used noise contrastive estimation in addition to trying out different nonlinearities like the rectified linear nonlinearity, and we showed that it works quite well for machine translation as well. So the key point, sort of the key point here, or the takeaway message is, you can actually train these models fast. And so when I say fast, instead of having to go over all the words in your vocabulary, you only have to go over k. You only have to go over k items. So in a sense, your training complexity is constant because irrespective of the size of your vocabulary, you could always just use 100 noise samples, and 100 seems to be enough. Whereas in the case of maximum likelihood, it's linear. Yeah, so this is essentially the probability that a word is true given the context is this sort of, it takes this form, and the probability the word is noise is this. So essentially what's happening is now your data is a bunch of true words and a bunch of noise words, and then you want to maximize this probability for the true words, and you want to maximize this probability for the noise words, and that's essentially what you're doing. Yeah, this is a classification problem now, binary classification problem, in fact. Your objective function, so you go over all your data, and you correctly classify, you want to correctly classify your true words as true, and you want to correctly classify your noise words as noise. Okay. Were there any questions? Yeah.
So you said 100 seems to be enough. You mean just the performance doesn't improve after 100?
Yeah. So performance from 100 to 500, you don't get as much improvements in perplexity as you do with 100. Like you might get a bit or two, if at all, but we don't. Especially when your training data is really large, just you don't need to go with that many noise samples. Yeah. So the way noise contrastive estimation. So again, Gutmann and Hjärvarinen were the two gentlemen that invented this sort of more general statistical estimation technique, and Min and Tay were the ones who adapted it for language modeling. So for each training example, you generate k noise samples. So in essence, your training data is sort of multiplied by k, and you train the model to classify real samples versus noise samples. Much faster training time, and there's this trick that you can use. You can actually kind of So one thing that I didn't talk about is what happened to the normalization constant. I mean, it's there, right? So what noise contrastive estimation does is it actually trains a value for the noise for the normalization constant as well. It treats it like a parameter in the model. And at the end of this training process, you actually get a value for z. The more noise samples you have, the closer will be this value for z than your actual, as compared to your true partition function, or the normalization constant is also sometimes called the partition function. It treats z as a parameter. Now you can do a training trick where you actually freeze z to be 1, and it's going to move the parameters in such a direction as to kind of encourage z to be 1. And now with regards to query time, this gives you a significant speed up because the normalization constant is 1. For all contexts, you essentially don't have to compute it. All you have to do is just compute, to go back here. All you have to do is just compute this quantity because the normalization constant is 1. And we've seen empirically, or at least, so I recently trained it on a much more complicated model, a recurrent neural network. And it was trained in about, I trained it with noise contrastive estimation on about 44 million words. And I saw that the mean of the log of the normalization constant over my validation n-grams was about 0.003. So the x of that is very close to 1. So it was just almost 1. And in our machine translation experiments as well, when we use this model at query time, at test time, so when we use this model at query time, we do not compute z anymore. We do not compute the normalization constant. So it's really fast. The only cost is just computing this, unnormalized probability. So to give you an idea, here's some results in the context of neural network and recurrent neural network language models, again on the same data set. Kneser and I was about 140. When we train a feed-forward neural network with maximum likelihood estimation, these results are from Mikolov, who trained these feed-forward. I believe these were feed-forward neural networks with sigmoid activations. I was able to achieve better perplexity with noise contrastive estimation. And I believe it was just 500 noise samples. So these are very competitive language models. And here's some results on code. So Sahil, student of Prem student, he trained the neural network language model. We have a toolkit available. There'll be links to it at the end of this. He took the data set of Android apps. It's about 11 million tokens. He created a 90-10 split. There was vocabulary. So I believe he took words with frequency greater than or equal to 5, which gave them about 50,000 words. So that's a very large vocabulary for the output layer. And by training using noise contrastive estimation, he was able to get about cross entropy of 2.95 on dev. So that's a I'm sorry?
Which is the perplexity of less than 8.
Yeah.
As opposed to 140 for core.
Yeah, certainly, yeah, it's true. So he was able to get very good perplexities. Unfortunately, I couldn't get sort of baseline like cache models in time. Turned out that we did train cache models. Well, they did train cache models, but they were on the entire vocabulary. So the cross entropy was higher because the cache model had to look at all the words and not just 50,000, so it was unfair to compare. But this does reasonably well and trained quite fast. I forgot. So you have to. So when I said train quite fast, we use about 16 cores. This you can compile the code with the Intel Math Kernel library, and things become quite fast because it has multi-threading built into it. So far, standard engram models, as I said, the model size is really big, great training times, good query times. If you train with maximum likelihood, then your model size is smaller, but you have poor training times and poor query time. NP, noise contrastive estimation training has benefits from these three properties. And we've seen empirically, at least on the tree bank, recurrent neural network language models are beating conventional count-based language models in perplexity. Yeah.
The model size of the NP-LM.
Yeah.
Can you please repeat the question?
Oh, I'll repeat it as soon as he says it. Yeah.
The model size of the neural network is a number of weights.
Exactly. Yeah. It's the embeddings plus the weight plus the matrices, but it's dominated by the embeddings, right? Because each word in the vocabulary has both an input and output embedding. You could share them, but we don't. In general, having them separate works better. And in general, if you actually having larger output embedding dimension than input is better. It learns better.
In this case, the model size is still a couple of thousands.
The model there was really small, but I have a model. I have a figure where I actually show the model size. It's so imagine if you had like 500 dimensions for 500. So I trained this on a vocabulary of 500,000. Somebody's actually trained it on a vocabulary of 1 million. He had a lot of time. I trained it on a vocabulary of 500,000, and each output embedding was about 750. So that's a large number. Those are the ones that dominate. Yeah.
Could you repeat the question again?
Oh, sorry. So the question was, how many parameters do you have in these feed for neural network type models? And the answer is, well, depends on how you actually set it up. But the number of parameters is dominated by the number of embeddings used for the words. Because even if you have 1,000 hidden units, two hidden units of size 1,000, you just have like a 1,000 by 1,000 matrix. But you could have a very large vocabulary, and you can dedicate 1,000 dimensions to each one of those words. So those are the ones that actually dominate. And I'll have a model. I'll show a model later on, and what were the dimensions that we used. So here's an example. Again, this is just sort of restating what I mentioned before. If you use NCE, then your training time is essentially constant, because you're just fixing the number of noise samples, whereas if you use MLE, then it grows linearly with vocabulary. So here's the model size. So I train a model with using about, actually, this is not 100,000, this is 500,000 words. And is that right? Did I mess this up? Let me see. So this would be, how would this make it to 90? If this was 500, so this has to be 500, yeah. So I had 500,000 input and output word vocabularies. This was the gigaword data set that I talked about. It's about 2.4 billion tokens, words. And I clipped all of them at frequency 6. So I got about 500,000 words. And the input dimensions for each one of these, one important point I forgot to mention. These embeddings across each one of these input positions are actually the same. They're shared. So each one of these input positions shares the same embedding, but they have different position context matrices, because different positions will have different contribution. The words that are seen in the past shouldn't have so much of an impact on the probability as the words that are seen closest to the output word. So we train different matrices, but each one of them actually, these matrices are different, but they actually share. And to give you an idea, there's a model by a very successful neural network model in machine translation called the neural network joint model, where you try to predict a word given 14 words here. And I actually sort of plotted the norm of these matrices, like squaring up all their weights. And it turns out, these matrices, and it turns out that if the norm just sort of decays like this. So you can see that the weights have, on average, have a higher magnitude on the matrices, the context matrices that are closest to the output word, and the ones that are farther actually sort of a smaller magnitude. So yeah, and so you get about these many parameters. No, that was correct. So if you had 100,000 vocabulary, then you'd get about 90 million parameters, and if you had a 500,000 word vocabulary, you'd get about 310 million parameters versus a billion n-gram parameters on the same data set. So I talked about these. People mentioned how are these. So note that every part of that model, including the embeddings, was trained. So we were training the embeddings, we were training the weight matrices, everything was being trained by trying to maximize the log likelihood of the data or trying to do this NCE estimation. So this answers the question as to how do we actually get these similarities. These things are trained. I took these embeddings and the output word embeddings, and I sort of, you can see here that these are the sort of 7 closest words in Euclidean distance to this word. So I looked at the embedding vector of this word. I think it was 750. Yes, it was 750. And these are the kind of k nearest neighbors, the closest words in Euclidean distance. So going back to our example, if we actually see that IBM was close to Apple and bot is close to sold is close to bot, so you would be able to kind of generalize or be able to transfer some information between these two contexts.
Can I ask a question?
Yeah.
Were there any attempts, maybe you can comment on language models based on embeddings, but not using it learning, not as neural networks?
Great, yeah. So the question was, were there any attempts to not automatically, could I rephrase your question as saying that, is there any way of specifying the features for these words manually or some other way rather than automatically learning them?
No, you can learn them, but not necessarily by neural networks.
Sure, yeah. So there's maximum entropy language models where people kind of decided, okay, here's a set of features that are representative, and they learn weights on those features. And you could potentially do that. In fact, you can. I think I can go back here. So you can think of this. So this is called a softmax layer. So this representation is the representation that the neural network decided to have for this context, right? I mean, you can imagine having your own representation based on your own set of features. It's just that this neural network is automatically learning which features are useful for words, but you could absolutely have your own. So it's like, you can think of it as, so these are called maximum entropy models that were actually successful. And you can think of the neural network as also a glorified maximum entropy model or an automatic maximum entropy model that tries to learn its own features for words. Yeah. Oh, wow, this is not clear. So, is this clear at all? Can people see or no? No, I'm sorry. This is, well, you know what? Prem is going to show embeddings on code, so that's going to be more exciting. But here we just took, there's a popular tool called tsni, and you take these 750 dimensional vectors for the words and you project them on a page, 2 dimensions, and it's nice because it actually preserves locality between the words. And here, David took all the words that ended with and sort of zoomed in. And I can see it, but I can tell you. So here it's slum, coliseum, auditorium, gymnasium, aquarium. Here it's Khartoum, Tulum.
You're having trouble too.
Yeah, well, because it's okay. Well, so here you can see there's a millennium. There's 2 different spellings of the word millennium right at the same place. Here's helium, polonium, cesium, strontium, cadmium. So elements here. What is this? Glum, bum drum, antebellum. Yeah, that's probably nonsense. But so here there's some names: McCallum, Fossum. Is probably a misspelling of McCallum, Blum. So you can see that it's somewhat reasonable. Now, these are not, you can get really excited, and one shouldn't think that they're necessarily semantic, but these are just sort of distributional similarities of words that are similar, like to co-occur in similar contexts. This is just how, I guess it's not interesting because the slides, these things just showing that on this large data set, it turns out that when you have enough data, you have to set these hyperparameters for these neural networks, learning rate, hidden dimensions, and it turns out that if you use different learning rates, it didn't matter so much. You kind of got reasonable perplexity on this very large data set that I trained. Other approaches, there are ways of actually dealing with this large output vocabulary, class-based softmax, hierarchical softmax. This is work that I mentioned. So I mentioned that there's a lot of hyperparameters, the hidden layer size, how many input dimensions you should have. And there's a paper by Kenton Murray and David Chang on automatically discovering the right size of the network. What does that mean for you? You just have to download the toolkit and use it. It's part of it, so it's great. As I mentioned, NCE, noise contrastive estimation, has also been used in modeling code and language. So it's actually turning out to be it's turning out to be a very successful and popular approach for training neural language models. So the last part is recurrent neural network language models, which I said trying to free you from this this fixed context. And here's so typically a feed-forward neural network can be sort of abstracted like this. You see a word, you generate the context vector, and you predict the next word. So a recurrent neural network is your context kind of depends on the previous context, which depends on the previous context, which depends on the previous context. So this maintains the history so far. And how does that work? Imagine you get a sentence and you intersect it with this recurrent neural network. And when I say intersection, here's how you compute the probability of the output word. You take the first word, predict cat, then you get a context vector. Then this is a language model, so you take cat, then you predict the next word. You update the context vector, then take sat, predict the next word. You have this updated context vector that's actually maintaining all the history so far. And how could this be useful? So imagine that you had this long kind of sentence, or maybe perhaps a passage. The cat sat on a mat. The cat caught a mouse. Now, if you just saw caught, it could have been anything. But because cat occurred somewhere in the past, it's probably likely that there was a mouse there. So these networks are capable of sort of being able to pick out necessary information from the past and using it to predict what the next word might be. Standard recurrent neural networks have these sigmoid nonlinearities. It's a squashing function. So what happens is you get this input, and this is the previous hidden vector. You just pass it through a sigmoid function, and which spits out a number between 0 and 1. And this is what you transmit. People also use these tangent nonlinearities, hyperbolic tangent, where it's between -1 and +1. How do you train these models? So again, similar, it's forward propagation and back propagation. You get a sentence. You compute the output probabilities. Similarly in the staggered fashion, where you take a word, predict the next word, then take the next word, predict the next word, so on and so forth. And then in back propagation, you actually send these error signals exactly in the opposite direction as when you did forward propagation. So the error derivatives for these parameters. And when I say parameters, the parameters again are these embeddings here, and there's some parameters, these matrices that are actually generating these hidden vectors. So you get these errors from all these points, and you sum them up, and you update the model, or you move the parameters in the direction of these gradients. Recurrent neural networks have this issue of vanishing gradient, that because you actually have this nonlinearity, you end up multiplying the gradient. So this is a squashing function between 0 and 1. For the sigmoid, the error, or once you backpropagate this error, the output here can be at most 0.25. And so what happens is when you keep multiplying it repeatedly, your errors could be really, really small here. So what people typically end up doing is that they only backpropagate the error. They do truncated backpropagation through time. They only backpropagate like some fixed number of steps. One solution is these long short-term memory recurrent neural networks, and this is I don't think I'll be able to go through this. But essentially, what I want to say is that the most important piece of this thing is this cell. The CT. So there we have this context vector. In a long short-term memory recurrent neural network, all the work goes on in trying to compute the cell value. And you can think of it as like as a memory in a computer. You're trying to update the cell value. And there's this, the process by which you actually compute the cell value is, you have this past memory that's coming in, just similar to the hidden vector, and now you want to be able to compute the cell value, or the current, you can think of it as the previous history, and this is the current history, or the previous memory and the current memory. So first you're going to decide how much you want to forget of the previous memory. It's just another sigmoid function. And then you do some forgetting. Then you decide how much new memory are you actually going to add. Again, you have an input gate that you first squash it, then you multiply it between 0 and 1, and that's how much new memory you're going to add. That's your current cell value. So this is how you update the cell. Then again, you need to compute output probabilities, and you need a hidden state. So you decide how much are you actually going to output. Again, very similar. You squash it. You multiply. You squash it. Then you multiply between 0 and 1. Scale it between 0 and 1, and then you get this hidden vector that multiplies and you're able to actually compute the probability of the output word. So it's sort of 3 steps. How much of the past memory you're going to remember, how much are you going to add, and that's how you update the cell. Turns out that if you actually look at how the error is being passed to the cell, you get this kind of error flow. This kind of error flow. And why this is good is because if you notice, if you actually look at the error flow over time, notice that there is no nonlinearity in the path of the error flow. So you don't have this vanishing gradient issue. The error is not passing through any nonlinearity. Versus in a recurrent neural network, they were going through consecutive sigmoids. So here, the error is just being added. So you don't have vanishing gradient. Your gradient doesn't become small. But you could get exploding gradients, which people have to deal with. LSTMs actually do better than even RNNs on this pen tree bank task. Chris, how much is that?
So I hate to cut you short, Ashish. I do want to point out that Ashish has done a really nice job of assembling tutorial slides, and the slides are available for download. We got started a little late. We're running late, so we're probably not going to have a chance to go through everything, but there's a lot of material in the slides that are published on the website. So I'd encourage you all to download that if you're interested in this area.
So we can kind of...
do you want to go? You have these nice sort of explanatory slides about what LSTMs are doing that I think.
So okay, we can probably just go through one of them and then sort of So like I said, these LSTMs are fairly complicated, but and people have been using them very actively without sort of and they've been at least in natural language it's been difficult to kind of see what's happening inside this cell or what is this cell really doing. So we try to so John May and I and a couple of folks at ISI. Where I work, we sort of try to look at simple problems and try to even see what these cells are doing. And what are these simple problems? So we use this architecture called the encoder-decoder. It's just, you can think of as 2 LSTMs, one after the other. So what happens is, imagine you're doing, this has also been used for translation. So imagine you get this input sentence in Esperanto and you want to actually produce the translation. This is an encoder LSTM. Each one of these is this LSTM block, those complicated cells and little forget gates and things like that. So you have these encoder, and what this encoder does is it eats up the sentence and produces a vector here, which it then hands off to the decoder, which does the job of generating the output translation. So this is the encoder-decoder. Was that clear? Basically, these are 2 LSTMs, one compressing the input sentence into depending on what your dimension is. And this is a sentence vector. Popular media, the people have actually also called it thought vectors in popular media. But you can think of this as a compression of the input sentence by the encoder. So we trained this on a bunch of very simple tasks. We're just going to, for the simple task that I'm going to show you just what's happening inside the internals. That's what's happening in the cell. And we're only going to train a single cell LSTM, a single cell, right? So what do I mean? So we're going to try this. We're going to train the following. Input 5 A's, output 5 A's. Input a single A, output a single A. So essentially, we're going to see, well, can it learn to spit out exactly the same number of outputs as the number of input A's? And we're only going to use one cell. So what does it mean? How am I going to feed it? So essentially, we need these start and stop symbols so that it can tell us when it's stopped. So you pad these. So in this case, you take in 4 A's from the encoder, get the sentence vector, or in this case, a single dimension, and then the decoder starts spitting out the output sentence, and then you have the stop symbol. So what we did was we again did some, we took training, validation, and test. We created some training data, randomly generated A's, input A's, and output A's, and we had some validation. And note that we only trained on sequences up to length 50, so 50 A's and output 50 A's again at most. And it learned it perfectly. The perplexity was like 1.00008 or something. And when we tested it on data where the sequences are actually longer, notice that it's not been trained on sequences length 50, but we tested it on sequences length 50 and it predicted it perfectly. So somehow it actually learned to do this counting automatically, even though it didn't see them, right? So it's not memorizing like, all right, for 50 sequences I need to do this 49. So how did it do it? So here's a visualization of what's happening in the cell. It's a single cell, so we can actually visualize it. So here's the input. It goes bottom to top. Here's the encoder, and this is the decoder handoff. This is where you hand off the vector to the decoder. So I don't know if this is clear, but you can see here's decrementing, and the decoder starts incrementing. and these values are about the same. So the encoder sort of counts, and the decoder sort of removes all those counts, and it spits out stop when it's removed enough counts as those were entered. And here, so you can see the cell value. Here, so notice that I could have initialized it in a different way, and instead of decrementing, it could have been increment. It could have gone like this, but that's just an artifact of initialization. It just got initialized like that. And so here you can see here's the cell in the encoder. It's counting here, and here the cell in the decoder is counting back, and they're about the same. So this is when it knows it's seen about the same number of A's as the encoder. So you can actually see that it's learning to count. It is fairly expressive. Here's another example, similar behavior. We tried it with feeding A's or B's, not a mix. So it needs to be able to produce exactly the same number of A's or exactly the same number of B's. We couldn't do it with one cell, so we needed 2 cells. And here's your A counter cell, and one of the cells was the B counter cell. I will not have time to go over what the interactions of the hidden states were, but they're interesting in itself. The funny part is the embeddings were actually flipped. It learned that for these are the same dimensions. For B, this dimension is negative. For A, this dimension is high. And this allows it to actually learn whether it's an A sequence, or just print out whether it's to recognize whether it's an A sequence or a B sequence. And you can also do logs. So we fed in A, and we wanted to output log. We wanted to spit out log of the number, or some constant times log of number of A. So here's this counter. Sort of decrements exponentially. It learns it automatically. So they're doing something, and they've been useful in NLP. They're later part of my slides. I won't have time. There's toolkits out there that you could download and train these on your for your language models. Yeah, go ahead.
There is a paper called Neural Turing Machines.
Yeah.
And they had a similar evaluation on reproducing the input and the output. And they showed a similar generalization performance where they tested it on sequences of length longer than the ones that were present in training.
Right.
But this is simpler.
Yeah, it's much simpler. So the question is, this is paper on learning a neural Turing machine, and they had similar evaluation where it learned to copy and it learned to sort. But those sequences are more complicated. They weren't as simple as this, and this is a single-celled LSTM, whereas I don't know if they had any bounds on the number of parameters. We sort of try to, what's the easiest thing you can learn with the smallest possible network, and let's take a look at it. Yeah. So yeah, I'm done. This is sort of the meat of the talk. There's 2 kinds of language models: count-based, recurrent-based. Recurrent count-based in this continuous space. We have these feed-forward and recurrent neural network language models, and there's a whole bunch of downloadable tools. You can look at my slides. That's it. Oh, these are all the folks that have helped me build this. My advisor, Prem, Sahil, who generated some of the NPLM stuff. John, the visualizations, Victoria, and John and I worked on the visualizations. Victoria and Ingong are my collaborators. Thank you.
So does the noise contrastive estimation also help speed up training for things like LSTMs?
Yeah. Oh, so so I have a toolkit for training LSTMs with noise contrastive estimation, and I've been able to train it on 44 million words with vocabularies of 78,000, and it learns really well. And we've just figured out how to put it on the GPU, and either it's in the toolkit already or it's going to appear. There were some tricks involved. Hopefully we'll be able to write a paper about it, but yes, it works, and it works well.
Have you looked at these gated recurrent neural nets, which are a little simpler than LSTMs?
Sorry, I should repeat the previous question. The question was, does noise contrastive estimation work for LSTMs? And the answer was yes. The next question is, have I looked at gated recurrent neural networks? And I haven't, but somebody else has. Prem has used this. Yandex is this really nice, very recent toolkit that trains gated recurrent units with LSTM on the CPU. So you should check it out. It's very cool. Prem has used it a bit. Yeah.
We always need these probabilities that are computed by language models, because if we don't, we can speed up training.
Sure. Yeah.
So in terms of versatility to software.
Yeah, you could just. So we don't need probabilities. Yeah, we just need. As long as the correct word. So so the question was, do we need probabilities, and can we speed up training without probabilities? So in some sense, noise contrastive estimation did compute probabilities, but it moved from computing the probability of one versus everything else to just probability of one versus something else, right? So you could imagine like just a model that's trying to increase the score of the correct word versus some randomly generated words. Yeah. Yes, exactly, which is what, yeah, right. But I believe even there, the number of, so I know that, so for example, I think Colabert and Weston like trained their model for a very long time, and I think they generated their random samples were from the entire vocabulary. So they were not probabilistic, sure, but, and again, their job was not to use them, they just used them, the embeddings, probabilistic model. So you want the correct word to be higher than everything else, and probabilities kind of give you there. You could train a non-probabilistic model, but perhaps at the end you might have to get probabilities out of it, or some kind of comparative number that the correct word should be higher than everything else. So in probabilities, it's easy. It's higher probability, and things have to sum to 1, so everything else is less likely. But yeah, you could train other models. Yeah. Any other questions? Okay. Thank you.